Diamondback terrapins are semi-aquatic turtles that live along the Atlantic coast of the United States and are classified as vulnerable, threatened, or endangered across different states. It is estimated that over 75% of their habitats have been destroyed due to urbanization in coastal areas, with some of the biggest threats that they face including road mortality, recreational boating, and crabbing. Wildlife tracking enables conservationists to collect data about animals' movements and migration patterns and develop plans to reduce habitat loss and slow population decline. However, the average cost for wildlife trackers is between $1,000 and $4,000, making them inaccessible for most wildlife nonprofits.
Hi, we are GT Gals and we are partnering with the Wildlife Movement Institute to build a low-cost tracker for diamondback terrapin turtles to help researchers everywhere in their conservation efforts. We developed a tracker that can collect GPS data and send it via long-range radio communication, or LoRa. It also has a low-power mode to preserve battery life when a turtle is not in motion or underwater. Additionally, the tracker is designed to be hydrodynamic and modular. The modularity reduces waste in the turtle's habitat and makes it reusable. Our design uses an accelerometer, GNSS, and LoRa modules, antennas, and a pressure sensor. The pressure sensor is used to determine when the turtle is underwater, and the accelerometer detects whether or not the turtle is moving. If the tracker detects a substantial increase in pressure or little to no movement, the device goes in a low power mode since it cannot receive or transmit anything when it's underwater, and to prevent sending too much duplicate data. We also added a reed switch and separate battery compartment to improve the usability. The waterproofing method we choose will waterproof all the components while keeping the battery and programming port accessible so that when the battery dies or the tracker needs to be reprogrammed, the user can do so easily.
The tracker was programmed using Arduino libraries specifically for the microcontroller and accelerometer. There are sleep and wake functions in the accelerometer library that take in accelerometer data. Then, based on if the turtle is moving or not, the tracker is programmed to receive GNSS data at a normal or slower rate. When the pressure increases to a certain threshold, the tracker is triggered to go into a low-powered state. For the flow of information, first data is collected by the tracker using the GNSS satellite network. Then it's transmitted to the Wildlife Movement Institute's database via long-range or LoRa radio, and then they have a dashboard that connects to the database where the data can be visualized.
The enclosure for our design features two main parts, the main housing and the attachment plate. The standard for attaching trackers to turtles is to use epoxy, but this means that to retrieve the tracker later, it must be sawed off using a Dremel tool, which is unpleasant for the researcher and invasive to the wildlife. With our design, the attachment plate is epoxied directly to the carapace of the turtle, and the housing is screwed onto the attachment plate. This ensures that the main housing and the electronics are easily retrievable. The attachment plate detaches later when the turtle sheds the outer layer of its carapace annually. The profile of our design was created using surface modeling techniques to ensure that it is hydrodynamic, decreasing its impact on the animal. A reflection analysis was conducted to ensure that the surface was smooth and continuous. Potting is used to waterproof the electronics so that the housing does not have to be watertight, but the battery remains accessible because it is enclosed in a separate waterproof capsule.
To choose the most effective technology to use for data collection and communication, we tested a flexible and patch antenna to collect coordinates and a Swarm module to test communication. Swarm is an independent satellite network and is a paid-for service that allows customers to send data wirelessly no matter where they are. The metrics we collected were related to precision, time to get a coordinate, accuracy, and time to send a coordinate. From our tests and considering the needs of our sponsor, we determined that the patch antenna should be used in the final design. However, the performance of the Swarm module was promising and could be a better solution in different applications where animals are traveling farther distances or through uneven terrain. To summarize, the main things we achieved were that we improved usability of the tracker by designing a two-piece enclosure and our chosen waterproofing methods, improved the battery life with a varied data collection rate, and validated different tracking technologies via experimentation. Future work could be to adapt the enclosure to different shaped turtle shells, process location data off the board to improve location accuracy, and integrate renewable sources of power to extend battery life. Thank you for listening. The GT Gals hope to see you at Expo.